Alright, so welcome to day 16 of Advent of Code, and today we are gonna solve a reindeer maze. It's a maze problem, and the goal is to solve the maze that a reindeer is gonna traverse and try to find the lowest score. So we arrive to the thingy, to the event, and uh, we decide to, okay, let's try to watch one of these games, and we are being explained the rules. So the reindeer starts on the tile S, and they are facing east, so they are gonna face right, I would say, and need to reach the end tile marked with E. So this looks like a pathfinding problem, or most probably is gonna be solvable with depth first search. And they can move one tile at a time and do that by increasing their score by 1. Okay, and they can never go into a wall. Okay, and they also can rotate clockwise or counterclockwise, so they can only turn left or right. They cannot do 360 no scopes and stuff like that. And turning costs 1000 points, so that's also an interesting one. So who knows, maybe just using BFS won't be enough, because the path that's going to be the shortest might have more turns, and we might want to get the path that's shorter. So in this case, maybe we should use Dijkstra from the start, just to not just to avoid that problem of BFS being like, okay, here you turned 7 times, so your score is already 7000. Okay, and yeah, here it says that there are many paths, but the best one is like this. So again, maybe we should just use Dijkstra from the beginning. Like, it's just gonna be, it's basically gonna be, let's just say BFS with a priority queue, right? So instead of here, for instance, when we choose the path, if we go up or straight forward, it's gonna be like, okay, if you go on this path, you'll have the score too big. So in the priority queue, this one will be put last, right? That's the idea with Dijkstra. We have to sort. So in BFS, you just put all the neighbors in a list, in a queue, and you take them in order. It doesn't matter. But with Dijkstra, the idea is to put them in a priority queue, so that the order matters. Okay, so what is the low score that a reindeer can get? That's pretty straightforward. I think let's just use Python or TypeScript for this one, I guess. So why not? Let's start up new Vim, and let's go to day 16. I have the one of the examples I copied. I think it's this one, or no, no, it's the last one. Okay, so it's the one with 11,000 points. Yeah, it is. Okay, so let's do main.py. Do I have even... I have LSP, nice. So let's try to solve this one. So I'm also going to use... I know it's kind of like Pygat, which it's not my thing, so... I don't know, I just found it on GitHub. It's a programming language made by some guy. Okay, so... yeah, let's just try to solve part 1 in Python. Perfect. So we are just gonna import sys, and let's do our main function. First, I should just do the hello world protocol. So hello world, and make sure that everything is set up correctly. The fuck? Yeah, I like to... so when you run nix develop, you have to specify the shell otherwise it just starts bash, and I'm not sure how to change that. Okay, so let's go to day 16 and let's try Python 3 main py, and at some point we'll pass tmp into it. Okay, perfect. So how are we gonna, I mean, I guess I know why people use, we can say read lines. So we get straight a list of lines. I guess I know why people use Python. It's just so easy to read the input in Python. Like, why would you even bother with anything else? Okay, so my plan is to build the hash map of the points. So it's, you can think of it as adjacency, like a graph. Obviously, we need to build this graph. So it's gonna be something like the index is gonna be a point, and the, or I guess the key is gonna be a point, and the value is gonna be list of neighbors. I mean, that's, I think, yeah. I think, yeah, that's how I want to build the input. So let's do parse input. Maybe I can just have input is gonna be a string, and we just return like a list. I guess we are gonna return a dictionary, and it's gonna be, you'll see what in a second. So let's just read the input, like std into a string, and then we have our puzzle is gonna be parse input. And I'm gonna be honest, like Haskell as well, it's so easy to read the input and print data. So I'd say, I don't know, it feels like it could be a good language to use for AoC, Haskell. If you like learn it a little bit. So input.split lines, okay, interesting function. Keep ends should be false. I think it's okay. So these are gonna be the lines, and let's try to do a for loop. So we should do for row in range len lines. So let's do it like rows. Line is gonna be lines of row, and then for column in range len line. So the point is a row and column, right? And I want to generate the neighbors and just check if the neighbors are dots, right? So the idea is to just check for the neighbors. So def neighbors, I think that's how you spell it, I don't know, point. And what do we want to do is, maybe we want to specify like directions. They are gonna be 0 1 0 -1 1 0 and -1 0, right? So these are the directions. So we can have even like point add, it's gonna be like point A and point B, and we can say something like point A0 plus point, I think we had them at, I already forgot, there was another day where we had to do this, I think yesterday, and Oh shit. And we did it in C. And you can already see the difference. Like, sure, it's easier, but you were questioning yourself, what are the types, right? And I think that's why C is pretty much just better for direction in direction, even though it was harder. I guess C++ is better at doing this kind of stuff, but I mean, yeah, whatever. So that's how we get the points of the neighbors. We just have to check that there are dots in the thingy. So we can have something like is maybe empty. Not even sure, because I want to check that the neighbor is also bounded. So I could just say let's have width is equal to, or I guess height is going to be equal to len lines, and width is going to be len lines 0. That's how you get the height and the width. So we can get all the neighbors. That's pretty easy, and we can filter them out based on if they are bounded or not. So we get the neighbors, and now we can say something like list filter. Maybe we can have is bounded and then neighbors, so we override it, and we can have here define is bounded. It's like a function inside of this function. Pretty cool, I know. So this one should take in a neighbor point, so n, and we can say something like turn 0 is less than, so first thing is going to be the row and the second thing is the column. So n should be greater than 0, n should be less strictly, so the row, than the height, and 0 is less than or equal to n1, and n1 is less than width. Perfect. So that's how we filter the bounded ones, and then we have to do is empty n, and we just say return lines. So we pass in a row, which is n0, and then n1, which is the column, So we get the row and the column, and it has to be equal to dot. Right, so that's how we know it's an empty space. Okay, so then we can filter again. Filter is empty ns. So that's how we are gonna get only the empty spaces, and then we can just say puzzle of point is equal to ns. So this is a dictionary from like a point to a list of points. Perfect. All right, so I guess the other thing is if not is empty of point, we can just skip it. Right, we just skip the points that are not empty, and maybe that's not entirely true, because a node is also empty if it's S or E. If it's S or E. So I might want to do this one like CH is equal to that, and then CH is this, or CH is S, or CH is N. So I think that's a bit better. Right, but I would also say that we need the start and end positions. Start is equal to none, and is equal to none. So maybe here if something like lines of row column is equal to S, then start this point, and if it's equal to E, then end this point. So we can save the start and end positions, and at the end we return puzzle start and end. So here is more like a tuple or something, but let's not do typing because typing again doesn't work anyways. So for the indirections, yeah. Whoa, I think I forgot to return. Okay, so we get some stuff. So for instance, here at 1515, it says that it has these two neighbors. Is that really true? How big is the... Maybe we should also return the width and height. 1718. So at least we know that the start is 15.1, right? So we can say maybe, let's do start and width and height, and we can say, okay, show me the neighbors of start position, and that's only, yeah, I mean, it's only 14.1. So I would say maybe it's correct, maybe it's fine. Okay, and I wanted the width and the height just to be able to like print the map if we need that, but I don't think we'll do. Okay, so the next step, which like that, come on, no one knows this algorithm by heart. It's like we only use it for advent of code. So I need at least the Wikipedia algorithm to solve it. Okay, but I know the idea, right? That you have a priority queue for the nodes instead of just keeping a queue, a simple queue. So for each vertex, we initialize the distance to be infinity. Previous is undefined. This is if we want to reconstruct the path. Maybe we'll just print it. And we add v to q. And then we say the distance from the source to the source is 0, obviously. And while q is not empty, we get a node from a queue with a minimum distance, so that's why we want a priority queue. So obviously the first one is gonna be the source, right? And then it says that for each neighbor, which we just built, still in queue, we do the following. We take the distance from the up until the current point plus the distance or I guess in our case it's going to be the score from going to the current node to v. So if we go forward, it's going to be 1, this graph.edges, and if we turn to the left or to the right, it's going to be 1000. And it's gonna be interesting how we are gonna deal with going back. Right, so we also need the facing attribute to be at play. Yeah. Okay. So we need to not forget about facing. So maybe we'll return facing, and facing, as they said, it's gonna be, let's think, so east, right? So if this is row and column, we want direction 0 basically, that's east. So we can say directions 0, so that's gonna be our facing direction. Okay, so we get the distance, so the distance function is gonna be interesting to build. And then if the alternative distance is less than what we have in our map, then we set it, we set the previous, and we add v to the queue with a new distance. Right, but did we remove v? I think we don't. Wait, let's think. I don't think we remove v. You only remove it once you choose it, so yeah, it makes sense. Okay, and this is just printing the thing. Okay, so let's see. So we need obviously Python pq, and this is a it's called heapq. It's just a standard library thingy, so we can just import it and we can have a priority queue. So let's implement part 1, and part 1 is going to take in puzzle, start, end, and facing, initial facing. All right, so what we need to do is that for each vertex, so a vertex is a key in our puzzle hash map. Vertex is like a node. It's another way of saying node, which, I mean, yes. So for key in puzzle, we can call it v just to be consistent with the Dijkstra thing. So for each vertex, we need to keep a distance. So it's gonna be distance is gonna be a dictionary, and this one is gonna be a dictionary from point to int or none. And if it's none, it means infinity. We can do something like that. And then we have previous, which is a dictionary from point to another point. So it's like parents map. Okay, so in here we are gonna say distance of vertex is infinite, and previous v is, I guess this also with none, like optional values. And yeah, I guess it's not indented properly, so it is what it is. All right, so we have to add v to q, and the thing is this. V to the q. I think we need to, so we heap push value. So yeah, I guess the q is also like gonna be, so did they call it capital Q? Yeah, so capital Q is gonna be just a list, and here we need to do heap push, heap, I guess heap push. Interesting. I remember you could also put like a key. But whatever. So the queue should have as a thing. So the queue and the items should be the distance and item itself. So maybe it's gonna sort them by like the distance if we are lucky. Something like this, right? We put the distance and V. No idea how they sort it by none. I mean, yeah, it's pretty weird that distance of source is 0. Oh, using a priority queue, right? That's my, so I guess the priority queue, yeah, it makes sense to just add something in it only if, I guess infinity. Okay, let's keep it like this and say if V is equal to start, then we do something, and on the else case, so previous is previous, on the, I guess list V is equal to 0, right? That's the only thing we do. And then if V is start, else none, so it's shorter, so it's the same thing. All right, and then we can do the while queue is not empty, so while, I guess we can just say len q is greater than 0 just to indicate that better. We need a minimum node. Wait, let's, for 1 second, let's print the queue. I'm curious to see if 0 is gonna be puzzle, start, and facing. I'm curious if, so we cannot really have none. Maybe we can have Python infinity. I'm pretty sure there is infinity in Python. You can do float inf or math inf. Let's do math inf. Okay, so maybe that works. Nice. So you can see this one is the first one. Okay, let's use inf. That's cool. So while this thing is greater than 0, then we extract the minimum. So let's call it u as well, just to show that. So we have to do heap q, heap pop from our queue, and that's how we take the minimum. Then for each neighbor, and now it's interesting, because in the distances map and also in the queue, we need to keep track as well of the facing direction. Right. So it might be even how we do this these hash maps. Maybe it's actually gonna be something like point and facing to the distance, and here it's point and facing to point and facing, right? Maybe because the facing direction is important, but it's weird because yeah, it's kind of important, but I guess so. I mean, let's not do previous because it's not relevant anyways, so. And then direction in directions, right? We could say that here we are gonna put V and facing, or I guess direction. And here if and D is equal to facing. And in the heap, we are gonna have distance VD and V and D as the item, right? So maybe we have to keep both the V and the D. But yeah, now it's a bit stupid that we created the puzzle. I mean, it's not really, because we can just filter out all the like points that are not reachable. So, for instance, would be so much easier if we can just say puzzle of U and just get neighbors. But we need to do some extra stuff. Neighbors. I think I already have this as a function. Facing neighbors, and it's gonna be puzzle, point, and facing, and it's gonna return the neighbors and the costs, right? So it's gonna give us a list of neighbors and the costs to get to them. So it's maybe like costs, so to speak, right? So we are gonna do something like ns is puzzle point. I mean, we could have built them beforehand, but no, it's fine. I was thinking we could have generated the neighbors like that here from the beginning, but like for each facing, right? And then puzzle would be a map from, like, instead of how it is now, from but I don't know, it's fine like this. So here we are getting the neighbors, and yeah, you know what, that makes even more sense to just generate them like that. So here it's point, neighbors point. So it would be something like for direction in directions, we generate neighbors of point and this D. We bound it, we check if they are empty, and then we say puzzle of point and direction is ns, so it's gonna look a bit different. All right, let's not do anything here. Let's just print puzzle first. I think that's making more sense. All right, so how is neighbors nd gonna work? So we know that we are facing in the D direction. So for neighbor direction in directions, right? If D is a neighbor direction, then the cost is 1 because we move forward, right? Then we need to check if it's rotated to the left or to the right. So that's like saying something like if D, so that's cost is equal to 1. Let's have ns is equal to an empty list. So I'm gonna say ns dot append, so neighbors append, and it's gonna be the tuple as well. So point add point and neighbor direction, right? But you know what I'm not sure in this thing is it goes up, and then there's, I mean, yeah, it's like whatever. So we append the point with a cost of 1, right? We append the point with a cost of 1. Then else, maybe else if, let's say if D is in the opposite direction, so I could say something like D0, or I guess minus D0 minus D1 is equal to ND. Then we just continue because it means it's 360 now, so it's like 380 degrees. And on the else case, we just append the point with a cost of 1000. And at the end we return. So that's how I think we should do neighbors. Let's see if it's actually working. Oh, so where do we do something? Is bounded. Aha. So for is bounded, this is neighbor and cost. So we can say neighbor is equal to nc. And here it's also neighbor and cost. So we can say neighbor is equal to nc. Wait, what? ns. What is in the neighbors? Where does it complain about it? On line 37? In is empty. Okay, so let's bring, I mean, what the fuck? Oh, and C, I'm sorry. 0, 0. I see, it's because yeah, I could just say that just to meme it. Okay, so we get some stuff. Maybe it's interesting to see what puzzle of start is. So like the starting position. Oh, it's like direction, or I guess facing, right? That's the entry point. Wait, what the fuck? And facing, I meant. So it's going to 14.1, but with a cost of 1,000. Is that really gonna happen? Or, you know what? Actually, I think that turning keeps you on the same place, actually. So what that means is that here, when we do turning, we keep the same point, actually. But it's like I need to keep also the direction. So it's point and new direction. Right, something like this. Okay, what the fuck? Okay, I'm gonna say then point. Oh shit. Let's do it like, yeah, let's do it like it's gonna be the point, the direction, and the cost. But it's better like this. So we are gonna have node and direction. Right, so here it should be like directions. It doesn't even matter, I can put a 0. Right, so it says that it can either turn up or down with a cost of 1,000. Right, I think that's kind of better. So the neighbors of the initial position looking right, it's staying in the same position and it looks up with a cost of 1,000, stay in the same position and it looks down, or with cost of 1,000. I think that's a better input, honestly. So let's just go with this one. So then, yeah, let's go back to our no, like if I do undo until we get back the code. I mean, it sucks anyway. So yeah, let's just start. So for a V in puzzle, so we go with all the vertices, and the vertices in our case are gonna be the position and the facing direction, right? So we get them in one go. We don't need to generate them anymore. So what we can do is say that distance of this vertex is 0 if V is equal to start. And I guess what's funny is that start is gonna just be, so if we try to print start is gonna be what we need. So math in So I think start is just gonna be, oh wait, start doesn't have the facing. Let me just add directions 0. I guess somehow it makes sense, but doesn't. Okay, so 15, yeah. Okay, and then we can heap q, heap push into the q. We can push basically dist v and v. So now if we print the q, we should see something like this. And then the first one is gonna be 0. Perfect. For the starting position. So while len q is greater than 0, we can do something like extract the minimum. So u is gonna be heap q, heap pop from the q. Hopefully it's minimum, right? Pop the smallest one, yeah. And then for each neighbor, we do some stuff. So for, and now that's the interesting part, for neighbor v. So for v in puzzle u, right? We just got the neighbor. We don't need to do anything. We need a cost. So alt is going to be dist up until this point plus, and if you remember, inside of v we actually have the v and the cost, so we just add a cost, right? And if this alternative is less than dist v, then we need to switch it, right? Dist v is equal to alt, yeah. And we need to put so we need to decrease the priority of v. That's the annoying part. Because how are we gonna find it? I mean, I could q dot remove v, right? But what was the right way of doing it? Heap q dot heap replace. But it doesn't know that the value. So we just need to decrease this priority. That's kind of annoying. Decrease the priority. That's what I would personally do. Just remove the item from the heap. But how are we gonna find it? Heap q dot heapify. I mean, I'm just gonna make a function def decrease priority, and it's gonna take in the q, the v, and the new cost. All right, so we can say decrease priority, maybe even q is equal to q v and alt cost. Right, but wait, is it alt cost or is it just, yeah, I mean it is alt cost. Okay, perfect. So what I'm gonna do is for like each item in the priority queue, so for you, so in the queue I said we are gonna have a cost, right, and a vertex. So we need to find this location where this happens. So I'm gonna say for something, or I guess index something, and like it's basically v, but let's say u in enumerate q. If v is equal to u, then we are going to say q of I is equal to cost and v. All right, and we can return heap q dot heapify q. Sadly, we need to run this stuff every time, which sucks. It's like sorting, but we don't have a decrease priority, like a real one. So shit. Let's print the dist. Let's see what's in the distance at the end. Key error. Wait, does that happen? 83. It also has the cost. So it's, yeah, important. Oh, what? I guess heapify returns none. Okay, so it's like sorted, like sort, I mean. Interesting, so it does something. I see numbers are a bit weird, but that's fine. What I'm interested in is basically for the indirections. So let's check all the options that we have in dist for the end goal plus the ending facing direction. So we want end and D here because we can reach the end in multiple ways, right? And these are all the ways we can reach it. Is one of them here? Yeah, it is. Nice. So, but again, we are interested only in the smallest one. So let's return minimum from this for the in directions, and I think this should be it. Print part 1. Wasn't this how you are doing it? It's like an if string. And what happens if we try our day 16 input? Oh, it's slow as shit. I guess mainly because of this heapify call here. How can we avoid that? How can we avoid that call? Yeah, I mean, that sucks. We can just at least print len q and see like progress wise. I mean, at least it's just decreasing. And yeah, it's like obviously some of the points are unreachable, but you still have to take them into account. Which is like the problem with Dijkstra is that it goes through all the points. It's not like A star, which tries to go to the goal as fast as possible. Dijkstra Python EQ. Is there a implementation of Dijkstra with heap? While heap. Okay, so let's see. Interesting. Interesting. So I guess the Wikipedia implementation is not the best one. We can try to do it like this. Right? I mean, it makes sense, but if node in distances, it's a bit weird. So distance, so it keeps the, distances is like just a dictionary, and then the heap is what we have. Then while the heap has some elements, it pops the distance and the node. If the node is already in distances, it's already encountered, but what if you can modify it? And it says we already know that this is, maybe it's like specific for a certain problem. Distances nodes equals to dist. So distances of for neighbor and weight in so yeah, neighbor and weight, right? That's what we have in our for loop. I mean, it's exactly what we do, right? We heap pop. We don't do this one, which, I mean, sure. For neighbor, if neighbor not in distances, let's try this one, right? Let's just try it. So the idea is, okay, let's keep the distances empty. And in the heap queue, let's just put like 0 and start positions, right? Let's just keep it like that. Then if what happens if we pop, let's keep that, I mean, no. Let's pop and let's try to follow the same logic. If node is already in distances, although I want to keep it like this. So this is the cost. If u in dist, we continue. Then dist u is equal to cost. It's a bit weird because it's, but whatever. So here we do a for loop over the neighbors in puzzle of u, and here it's the same. If I like that they are reversed, but anyways, so if v not in this, we heap push. So we heap q dot heap push. a little bit weird, but maybe it works. So we put distance plus weight and neighbor. So the distance is just u plus c, and the neighbor is v. No, I would be surprised if it's just this easy instead of doing the Wikipedia version. But I see the point of it's the first, like visit them in order, but it's like I'm not sure I got the error. So print cu. What's in c and u? Kind of useless. So c is gonna be 0 and u is gonna be the point and the direction. Okay, so this, as I said, it was point facing to cost, right? I mean, I'm stupid, it's the other way around. It's this one. Okay, so if u is in distance, I mean, it was right, actually, yeah. Point and facing. So dist facing is c, then we follow what's vmc here. I guess that's also right. Yeah. Wait, what? I'm working with the input directly, yeah. Let's do tmp. So if v is not in this, that's fine. We have, oh, we have the, no, like, I should call it weight. Plus weight. And yeah, that maybe is gonna do it. Oh, interesting. So it's still worked, right? Interesting. I'm curious, does it still work as well? Oh, so it's even so it's even easier than what Wikipedia says. You don't have to do the entire thing with. Interesting. So it's just basically BFS. So it was just BFS after all. Interesting. Okay, so let's see part 2. So now that we know what the best path looks like, what's the best spot to sit? So we know that every non-wall tile is equipped with places to sit along the edge of a tile. Okay, while determining which of these tiles would be the best depends on a lot of factors: how comfortable, how far away the bathrooms. The most important factor is whether the tile is on one of the best paths through the maze. Whether the tile is one of the best paths through the maze. Interesting. Okay, so you'll need to determine which tiles are part of any best path. 45 tiles. In the second example, there are 64 tiles. Oh, so how many tiles? So we need to keep the previous mapping. So previous, but let's just do it as part 2, right? So that's the idea. We just need to keep, oh, in the second example, there are 64 tiles that are part of at least one of the best paths. Also, there can be multiple best paths. Interesting. That's kind of more challenging, I guess. But let's try to see. So if we keep just the previous position, oh, it's one of those problems where you need to find all the paths. It's one of those. Yeah, I mean, how many tiles are part of at least one of the best paths? Because if we keep just the previous mapping, we'll find only one path. We'll only find one path. Yeah, literally no idea how to solve this one actually. Because finding like the first path, yeah, it's easy, but path finding on all paths, like it, I know there is an algorithm that gives you all the paths. Dijkstra is for finding the shortest path, but which one was for finding all the paths that are possible? Um, yeah, the Bellman-Ford algorithm computes shortest paths from a single to all other vertices. So to all the other vertices. Uh, Vertices, edges, vertex source. But I mean, I'm not sure if this one is useful, because this one just gives you like all the paths in the graph, but like find all paths between them, and that's like any angle path planning. Oh, this is, yeah, I mean, kind of weird. I mean, yeah, this one kind of sucks. Like, at least we can solve the first example, right? If we keep the visited, or I guess the previous map. So previous Should also be like a dict. And how do we actually set it? I guess something like previous of v is equal to u here. Alright, and for part 2, let's just print previous first. Okay, and what is the length of previous? And I just want to see it on TMP. What? Why is it like that? I guess with this algorithm it doesn't work really well. Like maybe it only worked for this one. Oh no, I guess, yeah, we have previous, but we have to actually, where was the algorithm to iterate previous? It's here, right? So maybe we can just use previous. Let's see. Def construct path gives previous and end position. So what I can do is have here, it says S is the empty sequence, U is the target, which is end, and if previous it's, okay, whatever, while U, so while U is not none, let's say, we can do something like S dot append U, and U is equal to previous dot get U. Right, and then we can just return S. So the question is if we can use this previous mapping to find all the paths from it. That would be reconstruct path, previous, and end. Now the problem is that here we also keep the facing direction in the previous, so I might want to first get a minimum. So m value is the minimum, and then something like for the in directions, if m is equal to dist of n and d, then we do this reconstruct path and we print s, we return 0. Maybe something like this. Wait, what? I guess u is equal to n here. Wait, what? Print and the value 1 and 15. Print u. Oh, so yeah, I forgot. It's and direction. Right, so we get a path. We get one of the paths, 60. But see, it was 64. No, yeah. In the second example, there are 64. $115, and there's the facing direction. like down for some reason. Oh no, it means up. So see, this is the, it went up, then it went up a lot, and then here it went to the right once, 2 times, 3 times, then it went down, down, more down. Yeah, so maybe we can play around somehow here and say that if v is somehow in the dist, so something like if v in dist, or I guess, yeah, if v in dist, so if we visited the v already, and distance of v, the distance up until v point is equal to c plus weight, we still say that previous of v is equal, but not equal. That's the idea. Previous should be a default dict then. Default dict. Collections import default dict. So we have a default dict, and in this case, what if we append u? Actually, what if we append u? So the idea is if we find a point like this, which is visited, but coming from this path gives us the same result, then we just say, okay, that would have been another way of coming here, right? So if it's equal, if the cost is the same, but we don't add it to the heap, we don't do this part, we just say, okay, let's just, so previous is used only here and here, and then here for reconstruct. And what if reconstruct is reconstruct paths? So this is paths, the same. So reconstruct paths is gonna be paths. Okay, so while u is not none, here we are doing shit. Here we do the following. So here we have, so here we start from the end, and it doesn't matter when we stop. So this is like use. U is end. So it's just a BFS at this point. Or is it? It's like we have a Q. Q is N. And pass. And while len Q is not 0, so while we have elements in the Q, we can say that U is Q dot pop, pop 0, pop the first item. Okay, we get the use or an empty list, right? And then for shit path. What the fuck are we supposed to do that? So we have a list of paths, we have a queue which contains only end in the beginning. We pop from there. We do something like yes previous get u and an empty list if it's not there, obviously. And then we have to iterate over the US's, right, over the points that we got, so they are the neighbors, so to speak. And we need to add them to the queue. That's a good point. We need to add them to the queue. And what are we gonna do with these points? So we add them to the queue, and I mean, we don't even need the path. Like we can just have a set and just add the points to this set. So for s in us, we just say q.append s, and when we pop something, we say paths.append or add s, add u. And here we can just say paths. So path is just gonna be a list of points that make up all the paths, I guess. So line 112. Wait, what? Key error. Previous of v. Didn't I say default dict? Oh, default dict list. But it's 81. Yeah, I mean, I'm not sure. I guess it has to be something like this, but I'm not sure yet. I'll have to think more about it, but I want to continue with this kind of approach. Right, so let's actually just try to print the map after we generate this path. Maybe I'm not generating them correctly, so let's try to do that. So what I'm gonna do actually is, wait, oh, I call this one also part 1. Funny. It should be like part 2 maybe. Okay, result 2, part 2. At least we have two different, I mean, it's Python, so yeah. Okay, let's do I guess we could just return paths, but I don't like that. I want to pass in the width and height here. Width, height. Even though it's not really just to be able to print this stuff. So I'm gonna say for row in range height, for column in range width, and we can just print something like a dot, and we can even say that the ending is nothing, and then print the new line. Right, so if I do this one, you can see it prints the map. Right, so now the idea is to print something different. If so, by default it's going to be a hash symbol, and if so if puzzle, what does, I forgot puzzle. Puzzle, I think it contained what are the keys of the puzzle? I already forgot. So it's also with the direction. interesting. So I guess it makes sense, right? But what do I want actually is just the points without direction. So I'm gonna say something like points is something like p of 0, let's say, for p in puzzle dot keys, but we don't need to say dot keys. So that's how I think we get the points only. Yeah, and then we can even do like list set, so we keep only the unique ones because we don't need to have all of them, right? So if row column in points, then we print a single dot, else we print a hash. All right, so this should show the map, but why do we have a two-liner at the bottom? I guess, oh, I know why. Is because when we parse input, we should also strip the input, but that's, you know, not the issue why we don't get the right answer. Okay, so that's one. That's the first part, and then we have this reconstruct paths. Right, and I guess for part one, so reconstruct paths. Let's try to make it like before. So while u is not none, we say paths append, and let's make it a list. Paths append u, then u is equal to get, and that's all. Right, and then we reconstruct paths, and we can just use paths down here. So we might have another one. So if row column in paths, then we print an O, like it shows in the example. No, it's not add, it's append, but different stuff. Unhashable type list. So in reconstruct paths. Wait. What? Ah, okay. Get or none of 0, something like, just to shit. What? So we have like a list of points, right? And the points are all of them like this. Huh. Oh, I'm wrong. It's paths that I wanted to see. So paths also have the directions. Alright, so I might be able to just do the same thing, paths, so we can see some stuff. Wait, what? Ah, paths. Okay, so you see that it's one of the paths that goes to the destination, right? And if we print len of the paths, we should see one of them, right? It's 49. So it's 49 points to get from start to finish with this one, right? Which is the up one. So what would happen now if we try, for instance, to say here -1? So we try to take the last point now. It goes on the lower one. See? That's interesting. So it goes on the lower path. So my idea is that why not just try to have like a queue like we did earlier. So q is equal to end, and while len q is greater than 0, then we say something like u equals to q.pop 0. So we take the first one, we add it to paths, then we have u is equal, so this is use because there are more, right? And then for s in use, then q dot append s, right? So this, if we print this one, we should see all of them, right? And it's, I get it. So wait, yeah, that's true, that's the right answer. So I mean, it's kind of, because here we get all the points, right? But yeah, that's true, that's the right answer. It doesn't matter which way you are facing. Oh, that was my problem. I was having, so here it was facing in two different directions, and here as well, or something like that. So that's what the problem was. So yeah, it doesn't matter which way you are facing when you build these paths. So yeah, that's the answer then, right? So the answer is just return len paths. Now obviously I would say paths is equal to this, and here we extend the paths because you might have multiple minimum ways you reach the end, so who knows. So let's see, and we get 64, nice. And if I do input day 16, we get 496, which is also correct. Nice, perfect. So yeah, that was I guess that was my initial mistake here. I was thinking that the facing direction matters, but for getting the paths, like for getting all the paths where you can actually sit and watch the show, it doesn't matter which way the reindeer is facing. We just care that it goes through that location. But for computing the actual minimum direction, yeah, the facing matters, but after, when you get the paths, it doesn't matter anymore. So yeah, I guess that's pretty cool. Yeah, it's gonna suck to build a visualization for it because I want to do that as well. Oh, and like a small Easter egg with this entire project. So if I go and I say nix run, we actually have, oops, I actually managed to do the thing in the terminal to work. I mean, it was working even before, but it was a bit suckier. But now we have day 15 as a game, basically. So yeah, that's kind of cool, I would say. Anyway, so yeah, that was it, I guess. I think going with Dijkstra was the right approach. And I guess, yeah, on the Wikipedia algorithm is not always the best one, as we saw. It's easier to just, like, my intuition was to solve it like this, But I thought, okay, let's just go through like explaining how, you would get it from Wikipedia. But yeah, my intuition was like, okay, we have the distances hash map and then the priority queue. We always pop the minimum distance, and then so it's just BFS with sorted neighbors. Basically, that's what Dijkstra is. And then, if you go recursive into the definition, you have to learn what BFS is. And if you really understand BFS, you'll be like, oh, okay, it makes sense now that Dijkstra is just we sorting the neighbors. So we take them in from the smallest one to the one that gives the largest score. So yeah, I guess that's it for today. We actually managed to solve both parts. It was more painful, but always for me, like these 2D search maps problems are the ones that suck the most. So yeah, I mean, I'm pretty happy that we actually managed to do it. Kind of sad that we wasted Python though, because yeah, but honestly, like, what other option would have worked here? Because I needed this heapq library that was, oh, you know what? Holy shit! If I think about it, ds.h, it has a priority queue. So I literally have priority queue implemented in ds.h. So even if we solve this one in C, it would have been pretty easy. And my priority queue implementation, I'm just gonna say it's much better than the Python one because you can actually put here a compare function. So you can sort the priority queue however you want. You are not limited to just, I mean, I'm pretty sure you can do that in Python as well, but let's not talk about that. Yeah, but would have worked in C as well to implement it, but again, we also used C already, so maybe WASM would have been an option because yeah, that's true. I could have done because we can compile ds.h to WASM actually. That's another, but yeah, we actually solved it. We wasted Python sadly, but no, it is what it is. So yeah, hopefully you found this one useful. Like even though I struggled a bit to finish part two, hopefully it makes sense why we did the previous coordinates like this and how we reconstructed the path. Like here we just did BFS, if you believe it or not. It's like solving the problem with two BFSs. So yeah, that's everything for today, and we'll see in the next one. So see you.